I think we are ready to start then. So, welcome everybody to the second day of the student presentations for the 2013 Shanghai Lectures. Um, we have quite a tight program today because we're already a bit behind schedule. So let's try if each of the groups can try to limit themselves to within 10-15 minutes for presentation and videos. So you can go through, well, you don't have to go through all the details maybe, and then we'll try to keep the question sessions a little bit short as well. We should try to finish by 1:30, and we also have an additional group that will try to present at 1. So let's try to keep it a little bit shorter than what we thought. We'll start with group 10, 2B, sorry, and then we'll try to fit in group 10 later whenever they can. So I hand it over to Philip and Michelle from group 2B, and also say hi to Tatiana, I can see there. And yeah, good luck, guys. We'll have some questions for you later, but it's quite it's not a very formal session, so don't feel like be afraid of saying something stupid. We're all here to learn. Good luck.
Very good morning to another person here. Approved by mentored by Martin, and members are Philip and Mike. The title is How Can Actuation or Locomotion Drive? So let's start. So the problem statement which is given to us is this, right? That is how to use sensing to drive actuation, and also how actuation also affects what you sense. So as you can see, the diagram is like there is a robot which is sensing its own arm, and then it is trying to recognize the image which is present in front of it. Actually, when it tries to perceive the image, it just takes it as a 2D object. It just takes it as a 2D object. So when the end effector of the robot, that is his arm, is going to touch an object, and when the object moves, the robot recognizes that it's not just or it's not just the representation. Also recognize that it is an object and it moves. So the position of its interpreter and the object which moves, the robot can perceive and learn. So here we are going to implement this mobile platform and try to test it. And this is a similar concept with also known as Swiss robots. So we are going to try to implement this with the help of a camera and a mobile robot, that is Pioneer robot, and we will try to simulate it with the web. So to explain what is the Swiss robot, let's go to this that you can get the view of. Are you able to see the video?
Yes, it's a bit slow, but
Basically, in this robot actually recognizes the box, that is movable box. There are two big movable boxes in the side of it. So the robot actually pushes all the objects and checks whether the object is movable or not. Then later on, when it tries to push the bigger object, it will recognize that okay, it's a movable object. So let's not try to push it again the next time. So while in the running, you can see that even though the robot reaches the rear end of the arena, it tries to avoid pushing that object because it already recognized that this object is not moving. So and this mechanism is used for clustering the objects, which we will see in the next slide. that is about more details on this robot. Here it was actually researched by Maris and Blockhaus in 1996. Actually, they were trying to explore some alternative design methodology based on exploiting constraints, and it was like created to consequences of morphology and interaction with the environment. It was inspired by the observation of social insect behavior, that is, a simple behavior rule could lead emergence to complex and intelligent collective behavior. They tried to explain this with a simple robot, with a simple morphology and simple control. They tried to plan this natural behavior in robot with the help of collective behavior, that is heap formation, that is the objects are all collected together, that is the boxes are all clustered together and form heap formation, that is they call this a strategy of that, and they use data bots for to perform this experiment, and later on this is known as the discovery. Let's move on to our main project, that is the title that this is the Kōan project which we are currently doing right now, and here uh, as you can see this is a sample of the world which screenshot of the world which has been what, okay. And then this is the world, and it's a square arena which is textured, and there is background which is also been given a texture of sky and hills. And then here we have the yellow and the blue boxes which are the objects. Yellow are the mobile one and 10 are the mobile one. There's two cameras, screens of the camera, the screens of the robot cameras. There is one you can see the front image and the camera over here on top. So here when the uh, simulation world which we are trying to implement on. Let's try to discuss on how the actuation drives engine. Like I'm not trying to discuss with on what we are trying to know. I'm just trying to say how actuation can drive engine. So, for example, let us take a robot A, which is having a static image processing, and a robot B, which is having a little more advanced, a real-time sensor, motor sensory motor coordination design for robot. So here, when the robot is in robot A, there is no real-time interaction with the world. That is it's already pre-programmed on what actions it will do when it recognizes this particular object. So the robot is not able to survive in the real world conditions. This is kind of a drawback for an case of a robot A. Whereas in the robot B, there is a real-time sensory simulation with the environment, and it can dynamically change the uh, program procedures in the real time, and it can recognize objects, and it can categorize the uh, objects in a group so that it can be more easier to implement and easier to interact with the real world. That is, for example, let us take an example of this robot which is how body shapes the way we when you intervene upward. That is, in that the example is like when uh, a robot with an arm, so it wants to pick up a coffee on a table. The robot can actually categorize the path on which it is going, the motion on which how it is going to take the cup from the table with its end effector, and how much pressure it needs to use while lifting the cup, whether it is empty or it is full. So these kind of uh, different actions can be categorized together to a particular goal oriented. So this kind of a sensory motor coordination can actually benefit the robot to learn the environment rather than a robot which is having a static or a pre-programmed basis. It will be a real difficult condition to perform the action. So, yeah, that's what we explained in this slide as the power of. So, when robot in this condition, in this project which we are doing right now, we are trying to implement this sensory motor coordination into the robot. That is with the help of camera image processing. Here, the movable and non-movable objects are recognized separately, and then the robot is acting according to according to the end world. That is, the robot is not known of the movable and immovable objects in the world, and the robot needs to learn which are all the movable and immovable objects, and then it needs to push all these movable objects outside the red mark line in the world, and then it needs to restore to its original position. This is the actual working which we're going to try put in this on project. So this implementation will be explained by Dev.
Yeah, here's the word again. As Vishal already explained, we have two types of objects. We have movable objects and fixed objects. The movable objects are indicated by the yellow color. The fixed objects are blue. And yes, so, and the robot has some behaviors in this world. And as we want to push the boxes around, we first want to try and to learn which boxes are movable and which boxes are fixed. So this is the first behavior. It's a learning behavior where the robot drives through the world and explores its world, and yeah, determines this different colors of the boxes. We programmed it so that the robot could keep track of multiple movable and non-movable boxes indicated by different colors. So there are two lists in the robot, where the robot remembers the different colors for both types of boxes. Then, when the robot learns that the color indicates one of the both types, fixed or movable, it starts behaving according to Breitenberg controller we implemented, and it follows the box or it avoids the box. And if the robot leaves the field, this was the red line here in at the end of the world. When the robot goes over this red line, it turns 180 degrees around and goes back in the field. And the same behavior occurs if it just bumps into one of the fixed boxes and comes into a state where it just can't move anywhere else because it's just pushing a non-movable box. So it then starts also to move around for 180 degrees and move in the opposite direction to explore the world again. Our idea was to push the boxes around of the of the world, like that it's falling down here the plane. Okay. So yes, and when the robot is in its turning behavior, which is also hard coded, it keeps looking for movable boxes. So if it starts turning and it discovers there is a movable box in its field of vision, it will start following this box or approaching this box. Okay. Do you have any questions so far?
Any questions? No, I think we're okay. And try to speed up a little bit. We're a bit low on time, if you can.
Yeah, sure, of course.
Okay, thank you.
Now, first, the behavior. How can the robot distinguish between movable and non-movable boxes? And to give you an impression how this looks, here we have a robot moving. Well, it tries to move along this towards this non-movable box. And here you see the frontal camera, and here you see the spherical camera, and you see that there's no motion. On the other hand, in this example, the robot starts pushing a movable box. The frontal camera doesn't change; it just has the color of the box. But here in the spherical camera, you should notice that an optical flow and the rounding of the robot. Now I'll start it again. You have a lot of movements. So here you have those movements, whereas in this example you have the still image, and it approaches the box and it stops. The whole optical flow stopped. So our idea was to calculate the difference between following images, and yeah, if there is a big difference in the images over the last 20 images, then the object is moving and the robot is pushing a movable object. And if there is not that big difference over the last images, we assume that the robot doesn't move because it's in front of a fixed object. And we're doing this by computing per pixel for each RGB channel the differences and summing them up and comparing it then to a threshold. So then I said the basic behavior is implemented by a Breitenberg controller. For that, we split up the frontal camera into vertically into two regions like eyes. So let me rewind. And here we see the behavior where the robot approaches a non-movable box. Then it should avoid it, like it does. And the normal way would be that it would follow this direction. But as on the right eye, he sees the yellow box, which is movable, and like it likes yellow and yellow boxes, it should now turn white, which it indeed does. So we have this, as I said, we have these two lists of colors in the robot, and it compares for each color if if it wants to follow this color or if it's afraid of this color. It's done by, it's a really easy approach. We did everything in WebBots. We thought about using OpenCV, but this was a bit too hard converting the images to from WebBots to OpenCV. So we did everything, the whole image processing in plain WebBots, and we simply used a calculated root mean square error between the color we know and we, in this case, for example, want to follow, and the average color of the whole image. It's like calculating differences over all RGB channels again. Yeah, and that's how we did it. And here's another example. Let me restart it. So in the first, at the beginning, the robot doesn't know anything about movable or non-movable boxes. So we designed the world that it will at first approach a non-movable box. It bumps into it, then it recognizes with the algorithm I already described that it's a non-movable box. It goes into turn around mode and turns 100 degrees around. It's not following yellow boxes at the moment because it doesn't know about yellow boxes. It only knows at this point that it has to avoid blue boxes and nothing more, and that it should explore the world. So it's exploring the world, we designed the environment such that it will, just after this turning around, bump into a movable box. Then it learns that this is a movable box. Okay, you see it will follow it anyway. Now you see that the box moved a bit, and you should now take a look at how the robot follows. Here's the robot follows the yellow box. You see it's a bit, it's flowing a bit to the left side, but it adapts to the motions of the box so that it can push it, yeah, down the road. So that's it. Yeah, the tools we used were just robots, plain robots, image processing, everything was on there. And yeah, that's it. Thank you.
All right, thank you very much.
Thank you.
All right, excellent. Thank you. Very nice presentation. We are ready for questions from the TAs. So anyone wants to start? I think Tatiana might have had a question. No, she's not there anymore. Anyone else wants to start? Damien, Neves, or Fabio? Okay, I'll start off with a question. So if we now switch or change the colors of the boxes, we put this robot in a different world with different colored boxes, where the boxes now, colors now mean different things, would it still be able to work as it did with these colors?
Yes, it's totally independent of the box color. So I mean, we didn't implement it like with the fixed color. It will adapt to every kind of color. It depends a bit on how different the colors of the different types of objects are, right, because we have ranges. Like for each value, it's an 8-bit value, and plus minus 5 integers. Right. So if the colors are distinct enough in the RGB channel, it's no problem, and it will adapt to all kinds of colors. We have also texture in the background, like you saw the spherical background with, right, the trees and mountains and stuff, and we did this such that we could get more differences when we are calculating the sums. But as well, if we would have just had a single color background, we would have the problem that the robot would have thought that it's approaching a movable box, because it's just the major color on the front camera would be the single color of the background. Right. So because of that, we implemented the spherical thing. But yes, I mean, you can have as much boxes and box colors for both types of boxes. You can't change the box types, but you can have as many colors as you want for those things.
Right. Excellent. Other questions?
What happens if there is a misclassification of one movable box as non-movable? For instance, it got stuck or some other problem. Will it be able to correct that error, or does it have to live with it?
Yeah, it's a good question. We coped for that when, for example, when we are approaching a fixed box, it first would think that the fixed box is a movable box, because when approaching it, you have big differences on the spherical camera. So it first assumes, by approaching a fixed box, that it's movable, then it bumps into it, and again assumes that it's fixed as well. So at the moment, then we fixed that by implementing thresholds. And we said that the image must be covered by like 98% with the color and the front color before it assumes that it's a movable or a fixed box. And I guess we could also implement something like that. We make the lists, well, that the color can just occur in one list. But otherwise, yeah, you would, of course, have some problems with that. But yeah, so far, well, we first hope just for this behavior, like or having a fixed box in those lists.
Okay. Any more questions? No more questions? All right, excellent. Well, really, thank you very much, Vishal and Philip. I really enjoyed your presentation. Really nice. You've done very well.